we're observing, it's cold and dry in the Atacama, and it's even colder in the South Pole, but it's really warm compared to a microkelvin, right? You're observing through a lot of atmosphere, a lot of background, and it's a great triumph for all of my experimental colleagues. And those of you who noticed just my leaning against these lights, I managed to almost turn them off. I claim no credit for any experimental success. My great contribution as a theorist and data analyst to the experiment is to never touch it. What we see, consistent picture, and this is another nice way of showing this, which is this shows the ACT and SPT data in green and red, the WMAP 9 years, flashing back and forth with the Planck data from the first Planck rules. And this is, again, looking at the amplitude of fluctuations versus multiple moment. This is angular scale plotted here. And now you can see the theory line quite nicely. And the theory and the data agree really well. Now, there's some interesting discrepancies, and we'll talk about them for a moment. And over here, it looks quite nice.
Would the recalibration of their fluctuation amplitude change anything?
No, because this is on a logarithmic scale. It actually agrees better. So, if I looked at there's an offset. The Planck points, the black points, if you notice, are a little bit below the line. It's about 2.4% below. And with the recalibration, it fits all the way through. It's a little bit low. This is a difference because it's a different sky cut, different fraction of the sky. What you're seeing here is what we call cosmic variance, we think. So when we look at the theory predicts what are the RMS amplitude of fluctuations. Remember I said the fluctuations are a Gaussian random field. And what the model predicts is the variance. So what it suggests is this is what you expect averaged over many sections of the universe for what we should get for microwave background fluctuation. When we look at the quadrupole, L equals 2, we're only looking at the quadrupole at 5 measurements of this Gaussian field. Because we have to throw out the galactic plane, it's actually really more like 4 measurements. So I toss the die 4 times. On average, I should get 3.5 for the average value when you roll the dice. But if you roll it 4 times, sometimes it's low, sometimes it's high. The quadrupole happens to be low. It's about 5% of the time you get something that low. That's intriguing, but most of us don't view 5% probability as something that's compelling. Usually in physics, science in general, you have something that's kind of, it happens 5% of the time. What you do is you do another experiment. And you get a more accurate experiment, and you measure it to higher precision, and most of the time the statistical fluctuation goes away. And every now and then it turns out to be really significant. We don't really get to do this here. This is not limited by our experimental noise. It's limited by the fact that we only see a certain fraction of the universe. And we don't get to make another measure. And a very intriguing thing is this pattern of multiples happens to be just right, that the angular correlation function goes to 0 at 60 degrees and stays there. There are no fluctuations bigger than that scale. And that could just be a statistical fluke. It's all consistent with statistics. Or it could be something really profound that we haven't figured out yet. So I like to point out that anomaly because this is all we will get to learn about the largest scales at some level. Another anomaly that I'll talk a little bit about, you'll notice out here, the data does differ, particularly around here. It differs a lot. Over here, it's not always going to be. And given how small the error bars are here, this difference worried me. And, you know, this is one of the things I focused on right after the Planck data came out, was the first look is you look at the Planck parameters. This is Planck measured with WMAP polarization. This is for the key parameters, how the amplitude of fluctuations vary with scale, what the density of matter is, what the density of atoms are, how fast the universe is expanding, the Hubble constant. And this, by the way, for the graduate students, when I talk to graduate students about giving talks, I tell them never do this. Do not put up large tables of values. But if you are, just keep them up for a while. And I think most of you look at this and you say, well, this is remarkably good agreement. These are two independent experiments, and they're getting answers that are consistent within a sigma. And you say, no, Planck was an improvement over WMAP and the ground-based experiments, but they did pretty well. The error bars, you know, did improve, but not phenomenally. But the thing is that these errors include cosmic variance errors. They include the fact that we only get to see a patch of the universe, and there's statistical fluctuations like we saw in the quadrupole. So the question to ask is, given these two measurements looked at the same patch of the same sky, how much should they differ? And they differ more than they should. And there are other concerns, and some of them persist. They're suggestive of, you know, here's a measurement of the amplitude of fluctuations versus the density of matter. This is from Planck paper 20. This shows the amplitude you measure based on looking at clusters. How stuff Ting does. You count clusters, you measure the amplitude of fluctuations, you infer an amplitude around 0.78 on the number most people are getting for the characteristic amplitude of fluctuations in 8 megaparsecs. This is the standard measurement. Planck was getting a value up around here. It shifted a little bit in their recalibration and things, but it's, you know, and this difference isn't even 3 sigma. But it's intriguing. And there's similar intriguing deviations. The best fit Planck value for the Hubble constant is lower than what people were getting from other measurements. So, you know, here's what we got from WMAP, and it's consistent with Planck. But, you know, recent measurements using Cepheids, or this is the Carnegie Hubble project, the kind of values that Sherry Suyu here was getting using strong lensing, they're all kind of up around here. They're a little bit higher. You know, and while it's progress that people argue whether it's 67 or 74 is the kind of limit of the small and large Hubble constant, the broad, you know, the high-level takeaways, they agree. But there is this intriguing tension. And this tension, you know, shows up in a bunch of different ways. These are a bunch of different ways of measuring the amplitude of fluctuations. This is taken from a paper by Frank van den Bosch. And, you know, here's measurements coming from galaxies and clusters, and this is from hot gas and clusters. And all these numbers were giving values around here. And the green was the WMAP error ellipse, and looked very consistent. When the Planck data came out, you know, it's consistent with the WMAP value, but it shifted away from what we were learning at lower redshift. And this isn't a huge discrepancy. It's not that we know that the model's ruled out, but it does suggest that this is worth paying attention to. And the response of my Planck colleagues to this tension was to say, we're right, there's a lot of systematics in these experiments, there's lots of things that need to be understood about properties of clusters. And on one hand, they're correct. There's lots of physics we need to get right to get these things. But I thought it was also worthwhile, and for a few minutes, I'm going to kind of dig into Planck data and show you some of the concerns why maybe there's something to worry about there. And one thing that worried me is this was from a Planck paper showing the deviation from the model. Each one of these points are independent. And while the chi-squared for this fit's acceptable, this, by the way, is a good lesson in why chi-squared doesn't tell you everything. There shouldn't be that many points off in a row that are independent. Right? This is an anomaly. Now, this anomaly that we wrote a follow-up paper to Planck with René Lozic and Raphael Flauger, we emphasized was worrying and did have effects on cosmological parameters. Now the Planck team has said, though they've not published corrected values, that this is due to the 4 Kelvin cooler light. The cooler for the Planck experiment vibrates, and it was vibrating at a resonance that was at that frequency and affecting the observations. And they, these are complicated, hard experiments. You're making microkelvin measurements. And they've identified this, and they've corrected it. My only complaint is they haven't, for over a year they've been sitting on corrected values and maps that with parameters that agree with somewhat better with ours, and they haven't released it. But anyway, we went back and went through this, and this was kind of fun to do. The Planck team's a really big team. The 3 of us on our own went through, Raphael and I reanalyzed the maps, René redid the whole Planck likelihood code, and we made a couple changes in our approach. I was very nervous about using in any analysis what are called autocorrelations, where you observe the sky at the same time and you autocorrelate 2 maps you make. We relied instead on an approach we use with the ground-based data, we use with WMAP as well, as using cross seasons. So we map the sky, so Planck mapped the sky twice in the day they released. We have 2 independent maps, taken 6 months apart. Noise is totally uncorrelated. You just measure cross correlations. If you have noise in the detectors, say due to vibrations, they're uncorrelated across that time scale. And I was pleased to see in the presentations in the Paris meeting that the Planck team has followed this approach in their final analysis, the one they haven't published yet that's coming out in January, where they're using the cross seasons. And this is something where it depends on who I talk to in the Planck team. But most people agree that they agree with our analysis. It's not clear whether their papers will say those words. I'm not, I made some friends and annoyed some people, I think, for the next 10 minutes of this talk. But I think it's really important. We learned a lot in WMAP from making our data public, having the community go through it, people redoing the analysis. I'd say, I don't know, 2/3 of the reanalyses that disagreed with us were wrong. People just didn't understand they did wrong. Another 6 did it a different way from how we did it, got something similar. That was good, maybe even a larger fraction. And then there was another small fraction, I don't know, 10% of 6, it's hard to quantify it properly, where people did something better than what we did. And they realized something we missed in some piece of it. And what we tried to do was learn from what they did. And it's one of the reasons WMAP 3 was better than WMAP 1, and WMAP 5 year better than WMAP 3 year, and so on. So hopefully we'll provide some of that role. And this just shows you how things change. So this was what the 2 columns I showed before. And for reasons due to the noise properties and the fact that it failed the null tests, I got very nervous about the Planck 217 gigahertz data. So if you just throw out the Planck 217 gigahertz data, rerun their analysis, these are the parameters you get. These agree remarkably well with what we were getting before. And it suggests all the shift is driven by 217 gigahertz. And we kept the error bars smaller by doing some things that allowed more sky. It shifted the Hubble constant a bit, so there's kind of shift. And so somewhat less tension. It shifted the amplitudes on the slide. It shifted the amplitude of fluctuations. So this was the old value, this was the new value. It's still on the higher side, but less tension. And what will be very interesting to see is when the 5-season Planck data is available, the error bars are smaller. Where does it end up in this space? Are the tensions worse? Or how does it change? I was going to give that talk when the results came out, but they're not out yet. But look for the papers, and then a lot of us will be looking at this carefully to see what's going on. The last part of my talk, I want to say a bit about polarization, and this will lead into my later talk a couple days from now, 8 days from now. So when we look at the microwave sky, we see not just fluctuations in temperature, but fluctuations in polarization. As the photons propagate to us, they scatter off of the electrons. And in one polarization, on an electron, you see photons that come in this way and scatter towards you in that polarization. In the other, you see photons that come in this way and scatter towards you. So a quadrupole that's seen by an electron at the surface of last sky in temperature translates into a polarization fluctuation that you see. So the temperature fluctuations get converted into polarization fluctuations. Polarization on the sky is a headless vector, and the polarization pattern we see can be broken down into two-piece types, what we call E-mode polarization and B-mode polarization. The E-mode pattern is symmetric under mirror reflection. You flip that picture, it looks the same. The B-mode pattern is antisymmetric. And you can decompose any polarization pattern into purely E-mode and purely B-mode. Variations in density, the dominant source of fluctuations we see in the temperature, produce only E-modes. Variations in polarization, gravitational waves, produce both E-modes and B-modes. And that's why the search for B-modes is so interesting, because it's a way of directly seeing gravitational waves from the first moments of the Big Bang. And with the Planck experiment having mapped the sky and temperature at pretty high resolution, while there's more things to be learned, particularly about small-scale fluctuations with things like clusters and gravitational lensing for the temperature, much of the focus in microwave background work, and a lot of what's been happening in the last year or two, and is going to happen in the next 5 to 10 years, is focused on polarization. Mapping the sky, learning what we can from E-modes, and then looking also at B-modes, both for looking at gravitational lensing, but fundamentally for looking at gravitational waves. And I'm just going to talk for a few minutes about some of the recent things we've been doing with the next generation version of ACT, called ACTPol, where we've been doing sensitive maps of polarization, and started to publish some of our first results from the polarization maps. And this is where you saw those whole sky maps. Here we're now going deep on relatively small fields compared to what you saw before, and making maps of polarization. And here are our published polarization maps, a polarization spectrum. This is now a plot not of temperature spectrum, but polarization spectrum. What's nice here is we fixed all the parameters from the temperature measurements. Given the measured temperature parameters, you can predict what polarization should see. Here's what's published in polarization. Planck has shown hints of their results and should publish them soon. These are more polarization measurements and the correlations between temperature and polarization. And the takeaway here is that things are fitting very nicely. Let me just quickly say a little bit about where we're going next with this experiment, which is just one of several of the next generation. We've been funded by the National Science Foundation to build what's called a medium MSIP proposal. It's a proposal of a next generation medium scale experiment. We're working on developing and deploying this right now. The plan here is to cover 20,000 square degrees, so a good fraction of the sky, completely overlapping with the LSST region, achieve 5 times Planck sensitivity, 5 times Planck's resolution. To do this at 5 different frequencies. Remember that you saw that for temperature, you had to worry about foregrounds, like Planck map things at 9 frequencies. Here the plan is to go for the set of frequencies and also make use of the Planck data. So you have in some ways 6 frequencies for characterizing a lot of the foregrounds. And this gives a sense of where we hope to be 4 years from now. And you can see how small the error boxes are in terms of our measurements of temperature and polarization. The polarization measurements are interesting for a number of reasons. First, they'll recheck all those parameters. They'll measure those basic cosmological parameters with an experiment like Advanced ACT to a factor 2 better than Planck. And, you know, while on one hand you might wonder, why do we really need to know the density of atoms a factor 2 better? I think we need to know these core parameters as well as we can, because we want to see if we have a consistent cosmology. And we want to see if we see evidence for new physics. And we can look for things like neutrino mass by looking quite sensitively for these things. And just, you know, we should be able to distinguish at, you know, many sigma between the expected signature of an inverted neutrino spectrum and a normal neutrino spectrum by looking at the amplitude. So the polarization will tell us in detail what's going on in the early universe. Because the microwave sky is actually quite polarized at small scales, it's about 17% polarized. On small scales, we should be able to get measurements on scales smaller than what we can measure in temperature. And that will tell us about the physics of inflation on smaller scales. Let us measure the amplitude of fluctuations versus scale more accurately. We'll also be able to look at E modes, look for gravitational lensing. This will give us a measurement of the amplitude of fluctuations. This lensing of E modes into B modes has already been seen quite nicely by experiments like polar bear, and then in cross correlation with small scale, with traces of large scale structure by us with the ACT experiment and SPT, and you know, it's almost certainly in the bicep data where you see this bump here. So a lot of experiments are now seeing this gravitational lensing effect. This is really neat because this will give us, across this region of sky when we take the E and B modes, we will have a map of the projected matter fluctuations between us and the surface of last scatter across this region of the sky with an angular resolution of better than half a degree. So we'll have, you know, over 80,000 points where we and we can cross-correlate with things like LSST maps of lensing. And we'll have something telling us what is the amplitude of fluctuations between here and that high region. And that's going to be very interesting for cross-correlation.
Why does the neutrino mass hierarchy affect polarization?
What the neutrino mass does is affect the amplitude of fluctuations. So, let me just drop here. If the universe was completely matter dominated, the amplitude of fluctuations would grow linearly with expansion factor. But neutrinos contribute to the expansion rate of the universe, but neutrinos don't cluster on small scales. So what that does is the growth of fluctuations is suppressed roughly by a factor that goes as 1 minus omega neutrino, what the suppression factor is goes as omega neutrino over omega matter. And because we've got about 8 e-folds of growth, the suppression factor is about 8 omega neutrino over omega matter. This scales with neutrino mass. So even in the case in which neutrinos have the minimal mass implied by neutrino oscillation experiments, there's about a suppression of 1% in the amplitude of fluctuations. That translates to a suppression of about 2% since we're measuring the power spectrum, in the amplitude of this power spectrum. So the amplitude of the what are my fluctuations in the matter fluctuations, and these are the ones that lens and couple E modes into B modes. By measuring that, I can get directly at neutrino mass, some of the neutrino masses. And what's nice is the oscillation experiments get the neutrino mass differences. And when we combine the two, we will have a measurement of all the neutrino masses. And that's coming. I mean, it's very clear that there are a bunch of experiments that are collecting data in the next couple years that we should have, within the next several years, I think, a definitive detection of neutrino mass through its effects on large-scale structure. There's a bunch of other things we can do with the experiment, but let me just move to a summary of where we are. Big picture, you have a successful model. With a handful of parameters, we get a lot of data. And it's a model that in some ways is simple, but in many ways strange. There's some intriguing possible deviations, and I think there's a lot of exciting things to look forward to, just first in the upcoming Planck data this month. And then the data is going to continue to improve from the ground-based experiments. There's some big open questions. Why is the universe accelerating today? That's about studying the properties of attention. Why was the universe accelerating in the past? That's the story of searching for gravitational waves. What's the dark matter? There's a number of key steps forward with CMB. Planck data should be coming at the end of the month. I've talked mostly about data from the Atacama, but there's also a very similar big telescope in the South Pole taking very interesting polarization data. The polar bear experiment's right next to ours and mapping at smaller scales. Xiaolin's can talk to you about the rapid improvement in the BICEP experiments, already made very sensitive maps of the sky, now going to higher sensitivity with BICEP 3. As we speak, the spider experiment, which is flying around Antarctica in a balloon, mapping the sky there. The longer the weather stays good, the more times they can go around, the better that will be. And my understanding is that's going well. So we're fortunate to be in a very interesting time in cosmology. We've got the standard model. It's got big open questions. And it's clear the data is going to get better. And as the data gets better, will this simple model still fit? Will we find new things?